This is already good enough circuit, but it has some minor issues. So we make small modifications in this ideal integrator, and we are making this as a practical integrator. So you can see the difference between the ideal and the practical integrator. What I did here, what is the difference? I add again the feedback resistor in parallel with this capacitor. So I just add one feedback resistor, then it becomes practical integrator. So I had given mostly the text also under, because during the lecture I am talking, but after a few minutes, when you look at that, you may not remember everything. So I had given the hint under each slide. So when you read this, you will remember what I say right now. Okay, the gain of the integrator at low frequency should be limited to avoid saturation problem. So when you apply the low frequency signal, the output should not reach the saturation immediately like this, instead of it go more up and then saturate, and then it immediately just move a little bit and then go to the saturation. So we do not want that at low frequencies. So this may, to avoid this, the another solution is we can increase the time constant value. So it means the R and C value should be very high. R and C value can be very large to achieve a perfect integration. What do I mean by perfect integration? Perfect means like I want the long slope. So, but practically to increase this RC value, it's not really possible. I cannot use in terms of kilo ohm maybe I can use. I cannot use in terms of mega ohms. So here I can use microfarad, or I cannot use several farad. So the capacitor will look like, practically it will look so big, and the heat dissipation will be very high. That's not good for the circuit design. So what is the alternate solution? So I cannot have this R and C value too high or too large to avoid this saturation problem. So the alternate solution is just adding this parallel resistor to this capacitor. This is called shunt resistor. Okay, so we have a problem only to integrate low frequency signals. So this is mainly because of the low frequencies. So, but we want our circuit to work either with the low frequency or high frequency. It's not a matter. So we are adding some extra devices or components to cope up or to work with any frequencies. So capacitor C will act as a open circuit at low frequency. That is why the problem is happening. So since we have this RF capacitor, so the low frequency is it's not really charging this capacitor. So low frequency will pass through this RF. That is the reason we are adding this RF. So this will avoid the saturation problem due to input offset voltage from node X. So input offset voltage is some kind of unwanted voltage. So we assume this Vx is equal to 0. Practically there may be few microvolt or millivolt that should not affect this amplification or the operation of the entire circuit. So this RF is really helping in many ways. So therefore we need to use a shunt resistor or parallel resistor. In case if there is any input offset voltage at node X, this can be handled by this shunt resistor. So this will bypass through this RF instead of affecting this CF charging. Okay, so this is the practical integrator circuit. So practical integrator circuit, the same one, just wrote it in a different way, and I added one more compensation resistor, R comp. Everything else is the same. Instead of just directly grounding, it's just going through a resistor. So here, this is the response of ideal integrator, the longest slope, but practical integrator, the signal will just move through this and then it will just go down. So here we have this 20 log RF by R1. So RF by R1. So here the value starts, and here we have the minus 3 dB. So from minus 3 dB, if you make just a dotted line, it will meet this curve at this point. This is called cutoff frequency. cutoff frequency. So cutoff frequency formula is 1 divided by 2 pi R of CF, R of CF. So then by changing this R of and CF value, you can change this cutoff value, cutoff frequency value. So we can call this as a FA or FC, cutoff frequency. In some circuits or some books, they use FC. In some books, they use FA. So why should we care about this FC value? I told you in the previous slide, we have a problem with low frequencies. So if you apply the signal frequency, input signal frequency, we are applying, this is the input signal. So input signal is definitely going to have certain amplitude and certain frequency, right? So if you apply the input signal frequency, that is the input signal frequency. For example, now let's say this is 1 second. So this is just like a 1 frequency per second, or 1 hertz per second. So if this input signal frequency is less than cutoff frequency, then it will act just as an inverting amplifier. Inverting amplifier means it will not care about this capacitor. Everything will just work like an inverting amplifier. So inverting amplifier, we know that how it works very well. So we know that. So inverting, the difference between inverting amplifier and this integrator is we are using the capacitor in the feedback. So at low frequency, the signals are passing through this RF and it doesn't care about this capacitor. So it means it automatically it's working as an inverting operational amplifier. So because we are calling this as an inverting because we are giving input to this negative. But if the input signal frequency is high, for example, if it's greater than cutoff frequency, then it will act as an integrator. Then you will get this slope. So, but after some time, it will reach zero gain at this point, the FB. It's called a 0 dB frequency. Okay, so here mainly you should remember cutoff frequency. When we talk about the filter design, we will talk more about cutoff frequency. But right now, you just try to remember cutoff frequency is important. Cutoff frequency you can calculate by using this formula, 1 divided by 2 pi RC. So here R of CF, that is because it's in the feedback. So by calculating this cutoff frequency, you will have an idea. What idea you will have? So cutoff frequency. So for example, I calculate cutoff frequency as 100 kilohertz. I am using this circuit as an integrator. So let us assume I am applying the input signal. This is the input signal with 50 kilohertz. I am the circuit designer. So I am just applying this 50 kilohertz as an input. Can I expect this circuit will work as an integrator? Definitely no, because I know I already calculated this capacitor, this cutoff frequency value by using this formula. I know what value I am using here. So I can easily calculate this cutoff frequency. So if I apply less than 100 kilohertz cutoff frequency value, then this circuit will not work as an integrator. It will just work as an inverting amplifier, inverting operational amplifier. So in that case, I will write in the specification or data sheet. So the cutoff frequency value must be more than this 100 kilohertz. For example, instead of 50 kilohertz, I apply 110 kilohertz. This is just for an example. So if you have some numbers in your mind, then you can easily remember the concept. So 110 kilohertz I apply at the input. Then what will happen? So now this circuit will work as an integrator. Because this is the high frequencies, then it will go through this path instead of here. Then this capacitor will start to store the charges, and then it will start to discharge. Then the slope will occur. Then we get the integration. So remember, the input signal frequency should be much larger than FA to achieve a perfect integration. So it should be minimum 10 times. So that is some kind of standard. You can also remember. So I told you this is 100 kilohertz, right? So if I apply 110 kilohertz, yes, integration is possible, but this is not a good integration. If I really want to have a perfect integration, perfect slope, then I should apply this input signal frequency 10 times of the cutoff frequency. 10 times of the cutoff frequency. So 10 multiplied by this 100 kilohertz. So what is that? 1000 kilohertz. Then this circuit will, this 1000 kilohertz I am applying here at the input. Then this circuit will work perfectly as an integrator. So here what I want you to remember is how to calculate the cutoff frequency, and you should apply the input signal frequency. It must be always more than this cutoff frequency. So just remember this. Practically, this integrator can also work as a low pass filter. I do not want to confuse you with the filter concept now. Just to remember, this is all about the integrator circuit. This is the problem for the integrator. So what is the lowest frequency limit of the following integrator circuit? You know, I call this as a lowest frequency limit because, as I said in the example, this is the 100 kilohertz. That is the cutoff frequency of this circuit. So if I apply below this value, then the circuit will not work as an integrator. So maximum I can go as the lowest, that is the 100 kilohertz. That is the cutoff frequency. So that is why the question is, what is the lowest frequency limit of the following integrator circuit? So please try to apply the formula 1 divided by 2 pi RF CF. So then you can find the value of this. If you apply everything, all the values, then you will get 159 hertz.